Hello everyone, I am Ember. Welcome or welcome back. On this channel we critically examine cults, conspiracies, and questionable science, such as today's video, which is about whether or not the universe is an atom. This seems unbelievable. Frankly, it probably is, but we're going to have a look at the science, quotation marks, behind it, and see if, in fact, we should decide whether we're living inside a molecule, or maybe there's little people living inside our molecules. It should be fun. It should be enlightening. But first, if you are new here, please take a moment to hit that subscribe button, because it helps a channel, a small channel, a newer channel, grow a lot, and we greatly appreciate it. So, thank you so much for that. And without further ado, let's hit it.
In the vastness of space, it's easy to feel small and insignificant. But scientists are getting freaked out by a new radical theory that suggests...
Scientists are getting freaked out. That's interesting. I haven't seen a freak. I mean, I have seen a bit of mild concern about recent discoveries by the James Webb Space Telescope, but I haven't heard of a theory that's causing anyone to freak out. But, you know, colorful language, let's see where it goes.
The whole universe is nothing but an atom. But what does that mean for us if the universe...
Okay, so there's a common misconception, and it's come up a lot, but there's a difference between a theory and a weird off-the-cuff random idea, right? Like, you can say, I have a crazy idea. What if the universe is an atom? And then we would want to look at that. We'd be like, okay, let's explore this. What are the implications? What signs do we have that this might be the case? But to call it a theory means it's been tested and evaluated and peer-reviewed and so forth. And I don't think it is that. It does not seem to be. Now, I have heard it come up in my high school chemistry class. There were a few people who noted that there's a certain similarity between the standard model of an atom with the nucleus and the electrons going around and the solar system. But even at the high school level, that only lasts for a few minutes before people realize that it's a superficial, circumstantial similarity that doesn't hold up at all. Like, for instance, atoms have charges. Like, the nucleus has a positive charge and the electrons have a negative charge. So to resemble a solar system, the planets would have to have a negative charge as well. And then there's covalent bonding, and planets tend to orbit along the plane of the ecliptic, whereas electrons go all over the place. So it just doesn't match up in any way, shape, or form. But maybe we've got more than that. I hope we do, because it'd be more interesting.
Is an atom. In this video, we dive into scientists' panic that the universe might be an atom. There are many patterns that are repeated throughout the universe. Take as an example the solar system, which consists of a huge star, the sun, and smaller planets that revolve around it. This arrangement is replicated many times over, with exoplanets orbiting distant stars outside of our solar system.
Okay, good so far. Planets go around suns. Yeah, I'm with you.
However, scientists noticed another unique pattern or similarity, the arrangement of the atom, which you were taught about in high school, and the universe. And this is why our universe may turn out to be an atom. Atoms are the fundamental building blocks of matter. Aside...
Hold on. No, they are not. Atoms... So the ancient Greeks believed that there was something called an atom, not the same as what we identify as atoms today, but there was a philosophical concept of a fundamental building block of reality called an atom. And it's fundamental because it's indivisible. Atoms, as we now understand them, are not either of those things. Like, they have components. You can break them down. Atoms have the nucleus and the electrons, and then the nucleus has protons and neutrons, and then the protons and neutrons have quarks, and it just keeps going. There, it it's such a throwaway statement, and he probably doesn't mean to mislead. He's just oversimplifying, but it's wrong on multiple levels, and it makes me worry about where the rest of this video is going to go.
From energy, everything in the universe is made of matter, so atoms make up everything in the universe. Because atoms were once thought to be the smallest things in the universe and could not be divided, the term atom comes from the Greek word for indivisible.
Yeah, there we go. Atoms are named for the old philosophical concept from the ancient Greeks, but that doesn't mean that they carry the same traits as the thought experiment of the atom.
Now know that atoms are made up of 3 subatomic particles: protons, neutrons, and electrons, which are made up of even smaller particles called quarks. So where did atoms come from? Atoms were created 13.7 billion years ago following the Big Bang.
Well, so yeah, following the Big Bang, I suppose, but not 13.7 billion years ago. So matter came into existence with the Big Bang, but we didn't have atoms for a very long time after that. It wasn't until something like 380,000 years later when the universe reached a point. The early hot, dense soup universe was a plasma. It was just raw protons floating around and electrons ping-ponging off of things. It wasn't until the universe cooled, that moment of last scattering that gave us the cosmic microwave background, that electrons were able to connect up with protons and form atoms. So the very first atoms were quite a ways after the Big Bang. And on top of that, many atoms, like carbon, are formed in the hearts of stars. And even bigger stuff, like uranium and plutonium, are formed in supernova. So there are atoms that came into existence much later because we needed to form galaxies and early stars, and then the stars had to burn, and then some of them had to explode and spread the matter all over the place. And so it wasn't until much later that some of the heavy elements were formed. Now, they were formed by the fusion of 2 existing atoms, but those atoms, they weren't uranium until that moment. So the uranium came into existence at that moment, not at the Big Bang. And it's important.
As the hot, dense new universe cooled, conditions became favorable for the formation of quarks and electrons. Quarks combined to form protons and neutrons, which then combined to form nuclei. According to CERN, this all happened within the first few minutes of the universe's existence. But it would be a while before we had the first atoms. It took 300...
Isn't that what I just said? Like, am I crazy? Is this narrator contradicting himself, or does he just not realize, or like what is happening? The whole reason I said atoms don't form until after was because he said they were created in the moment of the Big Bang, right? Or I may be losing my marbles, which apparently are also atoms. I mean, they're made of atoms, but you know what I mean.
180,000 years for the universe to cool enough, for the electrons to slow down enough, for the nuclei...
Electrons don't slow down. The electrons... Okay, so there are ways we can make electrons slow down. Because they have a negative electromagnetic charge, we can use electromagnetic fields to alter their speed. But all other things being equal, electrons move at the speed of light, just like a photon. That's the speed they move at, period. So they didn't slow down enough to be captured by an atom. They had too much energy to be captured. They were ping-ponging around between protons and so forth. It wasn't until the universe reached a certain point of expansion where the early protons and neutrons and so forth were separated enough that they could lose enough energy that the electrons eventually ran out of steam and were able to couple with the protons to form atoms. It's not a matter of speed, it's a matter of temperature, which it's energy level, but it's not. You're still going the same speed, both before and after, is what I'm getting at.
To capture them, thus forming the first atoms. The first atoms were primarily hydrogen and helium, which is still the most abundant elements in the universe. Gravity eventually caused clouds of gas to coalesce and form stars, and heavier atoms were, and still are, created within the stars and ejected into space when the star explodes as a supernova.
I feel like there's an echo in here. It's weird that this video is like, it's saying something wrong and then immediately saying something contradictory to that to correct it. And then it'll say the next wrong thing. And I don't know. It's a little sus.
Protons and neutrons are heavier than electrons that are found in the nucleus of the atom. Electrons are extremely light and they exist in a cloud around the nucleus. The radius of the electron cloud is 10,000 times that of the nucleus. Protons and neutrons are roughly the same mass. However, one proton is approximately 1,835 times heavier than an electron.
So that's important to note. We only have an approximate weight for proton, like a raw proton, a proton by itself, a hydrogen ion. We have an exact weight for. But as an atomic nucleus gets bigger, the weight per unit changes, because when you fuse two elements together, two hydrogens plus two neutrons to create a helium, or anything else, whenever you fuse two things together, you release energy. That's how fusion bombs work, is by forcing elements together, and it releases energy. There's also a mass loss involved. That's E equals mc squared at work. A portion of the mass gets turned into energy, and that's where the energy comes from a nuclear reaction. So the bigger the element you build, the more mass has been converted into energy through numerous fusion events. And so the less mass you have per unit in the nucleus. And I have a feeling that might be important. It might not, but it might be.
Atoms always have the same number of protons and electrons.
No, they do not. So if you have an atom, say you've got a helium, right? You've got two protons, two neutrons, and two electrons. If you take away an electron, it's still helium. It's just an ion, because now it's no longer overall neutral. Now it has a charge. Or if you add an extra electron and get it to stick, now you've created a negative ion. And yeah, ions are a thing. You don't always have the same number of electrons as protons.
Proton added to an atom creates a new element, whereas a neutron added to the atom creates an isotope or heavier version of that atom. You might be surprised at how long humans have entertained the idea of atoms. Democritus, a Greek scientist and philosopher,
That's the guy. He's the one who came up with the thought experiment about atoms. But again, his atoms are not the same as what we understand in the modern day to be an atom. We took the name from his thought experiment because it seemed to match what we were looking at the time, and we've since learned more, but the name stuck. It does not mean they're the same thing.
Developed the theory of the atom as early as 440 BC. Democritus's theory of atoms was most likely based on the work of previous philosophers.
That's weird that he says it's based on the work of previous philosophers, but he's the earliest on the chart. I mean, it very well could be. It's highly likely that other philosophers like Plato posited that all things are made from the forms of things. And yeah, so there's a lot of thought work that might underlie that, but it's not really important for our purposes today. I want to know how the universe is an atom.
Democritus begins his explanation of the atom with a stone. A cut stone yields two halves of the same stone. If the stone were continuously cut, there would eventually be a piece of the stone that was too small to be cut. The term atom is derived from...
Hold on. If you cut a stone, okay, and then you take a half and then you cut that, and then you take a half and then you cut that, and so on until eventually you can't cut it anymore. That's not because you've reached some uncuttable fundamental piece of stoneness, the quintessential element of stone. It's because you've reached a point where your cutting tool is a limiting factor. You're eventually going to get a piece of stone so small that your chisel can't split it. That doesn't mean it can't be split, just that you've reached the limit of your tool, you know? And that's kind of true with what we have going on today. Like, we tend to think of quarks or possibly bosons as the smallest particles, but it's because that's the limit of what we can cut today. We can smash protons together in big colliders like the Large Hadron, and we'll get quarks and other bits scattered all over the place, and it's very fascinating. But that's the limit of our ability right now. We can smash quarks together. We can, and you know, you've probably heard about the search for the Higgs boson, and that's what we did, is we smashed stuff until eventually we got an unidentified particle, different from anything else we've already identified, and we were looking for an unidentified particle, or well, we had characteristics in mind for the Higgs. We were like, it should do this and this and this. That's not exactly how it went down. We found a particle that we didn't recognize, and we were looking for a particle that had not yet been found. And so we went, that must be it. We predicted there'd be one more particle. We found one more particle. They must be the same particle. We're still to this day not sure that that mysterious discovered particle matches the properties of the Higgs, but that's a whole side discussion. The point is that with the best cutting tools available today, that's as small as we've been able to go. It does not mean there is nothing smaller, just we're at the limit of our technology. The same with Democritus' stone cutting analogy. You reach the limit of the chisel, that doesn't mean that's the end of the road, that's just the end of the usefulness of the chisel.
The Greek word for indivisible, which Democritus concluded must be the point at which a being, any form of matter, can no longer be divided.
Why is there an image of a human up there? Are we trying to imply that humans are... I'm pretty sure. I've seen magicians divide humans. Like, humans are not atoms, most definitely.
His explanation included the ideas that atoms exist independently of one another, that there are infinite number of atoms, that atoms can move, that atoms can combine to form matter.
Obviously, we know there is not an infinite number of atoms. That's just not how anything works. But that does have me thinking, the fact they threw the human on the screen earlier, that has me thinking, what if their proposition, the universe is an atom, then how could there be people on a part of a subparticle of an, like, you get down to a certain point, you're probably going to find a fundamental element or fundamental building block of some kind. And like, what? How can you be like, let's put people on it? Okay, but what are the people made of? Like, how does that work?
But do not merge to form a new atom, and that atoms cannot be divided. However, because most philosophers at the time, particularly the influential Aristotle, believed that all matter was made up of earth, air, fire, and water, Democritus...
Okay, Aristotle gets a lot of flack for the things that he got wrong, but a lot of what he got wrong, he didn't actually get wrong. Like in science class, way back in high school, one of my teachers made a point of making fun of Aristotle because he believed that all the planets made sounds. The music of the spheres was the concept. And obviously that's wrong because there's no air in space for sound to travel through. But that's not right. Like, first of all, just because there's no air for the sound to travel through doesn't mean no sound is being produced, you know? But even more importantly, everything above absolute zero vibrates. We've discovered this. And so we've been able to take readings and trace the vibrations, the frequencies of other planets like Jupiter, like Saturn, and then translate those vibrations into sound waves. So right now today, you can look up and download an MP3 of the sounds of Saturn. So even with the fact that there's no air in space, we were still able to retrieve sounds from these other planets. We can listen to the music of the spheres today. So it's not that Aristotle was wrong about that, just that the way we think about things isn't very flexible. We're in too much of a rush to say, oh, well, that guy was an idiot. I'm so much smarter than him. When in fact, if you look at it through the lens of what we understand today, a lot of these things turn out to be actually correct. The earth, air, fire, and water, for example, that's another one that the ancient Greeks get laughed at. Oh, well, obviously there's way more than 4 elements, and water itself is made of elements. Earth is made of elements. Okay, but you're being very literal about this. Let's consider it another way. The Greeks were not aware of the periodic table. They were not considering things in terms of hydrogen and carbon and silicon and so forth. They were considering what is matter. And they're looking at it and they're going solid, liquid, gas, plasma. Just because they were called elements, and that isn't the same as what we call elements today, doesn't mean they were incorrect. Because we learn today solid, liquid, gas, plasma. They weren't wrong. It's just a matter of how things are labeled and realizing that they're not talking about what you think they're talking about.
His atomic theory was abandoned. Now, one of the easiest similarities to spot is between the atom and the solar system. Every atom...
Oh, fuck, he's gonna go there. The atom and the solar system are similar. Like I said at the beginning of this video, they're not. They're not even remotely close to similar. And a 7th grade science student sees it within minutes of proposing the idea. So do not tell me scientists discovered this and are panicking over the concept. That's absolutely crazy.
According to the Bohr or solar system model of matter.
No. The Bohr model is not called the solar system model because it's nothing like a solar system. Like, it isn't even a superficial resemblance. Whatever. Let's just go on.
It's made up of a nucleus and a number of electrons that orbit around the nucleus. The nucleus is significantly larger than the electrons. These particles are thought to be small spheres or balls. This is similar to a solar system which has a large sun in the center and planets rotating in orbits around it.
No, you can't say big thing in middle, stuff go around, therefore same. That's not how anything works. Like, oh my goodness. So, like we talked about earlier, an atom has a nucleus and the electrons go in all directions around it. In a solar system, the planets tend to be along the plane of the ecliptic. Also, a nucleus has a positive charge. Does the sun have a positive charge? The electrons have a negative charge. Do the planets have a negative charge? All electrons have the same properties and traits. Do all planets have the same properties and traits? And what about moons? Like, if all the electrons are orbiting the nucleus, how do you get a moon around an electron? Like, none of this holds up to even the slightest bit of scrutiny. I hope he can do better than this, because I am not impressed.
Consider the element oxygen, which has a nucleus and 8 electrons in orbit. Our solar system consists of our sun and 8 planets.
Holy cow. Yes, our solar system has 8 planets because of what we defined as a planet. We created the definition and said these things are planets and these things are not. If we came up with a slightly different definition because we felt like it, Pluto would be a planet. And probably Ceres, the giant asteroid that's now also a dwarf planet. And possibly more things out in the K-belt that qualify as dwarf planets today might have made the cut and be considered planets. So you can't point to the fact that there are 8 planets as some kind of objective fact when it's our arbitrary definition that determines what is a planet. Like, I'm gonna need some headache medicine for this video, I tell you.
Orbiting it. Is it possible that the third electron from the oxygen nucleus is similar to our Earth, but on a much smaller and different scale? Perhaps tiny little people or animals are living on that electron.
I was just asking about this. How, if you had an electron, would you get tiny little people on it? Like, I swear, whoever wrote this, and it's not just the narrator, there's a whole production team behind this video, but that person, the writer, the lead writer at least, had to be very high. Like, hey man, what if the Earth, what if an electron was like the Earth or something, and what if people lived on the electron, man? Like, what would they be like, man? Like, oh my God.
When they peer through their tiny telescopes at the other atoms and molecules around them, they may believe they are viewing the entire universe. We can even fit Pluto into this model. It was once thought to be a planet and it does orbit the Sun. However, it's no longer considered a planet and it could have been a large asteroid captured into orbit by the Sun. Well, just as an extra electron in orbit around the oxygen nucleus would turn the atom into an ion.
Okay. So Pluto makes the sun an ion. Okay. So now the solar system has an overall negative charge. That's fine. What about covalent bonding? Like, is our solar system bonded to another solar system? Like, none of this holds up. Like, go back to the tiny people on Earth, right? They're looking through their telescopes. What are they seeing? The photons that exist in reality are the same size as their whole planet. And, oh, my goodness. So, photons by definition are the smallest amount of light. That's where quantum physics came from in the first place. Quantum, it's from the same root as quantity. We were trying to figure out how to measure the energy, the electromagnetic radiation put out by stars. And it was giving us a whole lot of trouble. So we went back to the drawing board and we were like, okay, what is the smallest possible amount of light that pieces of matter, which the sun is made of, could emit? And we found from study that you have to get an element excited to a certain point to get it to emit a photon. It'll reach a temperature and then pew, out goes a photon, and then it'll settle back down. You excite the electron, you move it up to a higher energy state, and there's certain stable states that we can calculate and predict. So a photon is the smallest amount of energy that can be emitted. That's what the definition is. So that gave us the ability to calculate how much energy is being released by the sun, and it was a very useful thing. But it's still a concept. It's not a real thing. It's our term for that minimal amount of energy. It's not actually... Anyway, that's a side topic. But that is it. You cannot get smaller than that. You cannot get less than that. That is the minimum. So if you have people living on an electron, and electrons, by the way, like photons, are a quantized unit of energy. They're not actually particles. They're waves. They're energy fields, just like photons. We visualize them as particles to make our models easier to understand, to make our math work more easily. But that's not what they actually are. Just because a photon can be emitted one at a time, one quantum of electromagnetic radiation, the photon itself is just a mental construct we use for our math. It's actually an energy field. The same with electrons. So I think people have completely lost track of that. They've confused the model for reality. And so they've written this narrative that what if electrons actually were tiny little balls that you could put people on? But, I mean, if a photon is the same size, how does that work? It doesn't make any sense.
An extra asteroid rotating around the Sun would turn the solar system into a type of solar ion or similar. Following that line of thought, solar systems could be atoms in a much larger universe.
I would very much like to see solar systems combine into a solar molecule, to see several suns link up like a long organic chain of carbon, and hydrogen sticking off everywhere. Like, we don't see that. That's not a thing that happens. So, but it would be fun to see. Also, it would be fun to see, bigger, heavier elements with big nucleuses. They decay, they're unstable, like uranium. Eventually it'll break apart. So I would love to see a giant sun, instead of going supernova, just kind of split, and each new mini sun take half of the planets with it. And also, do these giant suns supposedly have 92 planets or something, or whatever it is? It just... wow, none of this holds up at all.
Some stars are much larger than our Sun, while others are much smaller, just as some atomic nuclei are large and others are small, depending on their atomic number and weight. The rotating galaxy.
So, yeah, some stars are much, 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 much larger than the Sun. But the order of magnitude doesn't follow. Like, an element 92 is something like 180 times more massive than a hydrogen, an element 1. But there are stars that are way more than 92 times bigger than our sun. And also, like, wow. So, would radioactive decay, where the element splits, and then some of the mass is converted into energy, would that be the atomic equivalent of a supernova? But that doesn't create any new elements. It doesn't shove any new elements out into the cosmos. It just... wow, it's trippy. It's so trippy.
Galaxies may be analogous to rotating eddies in a liquid or gas. Given this resemblance, is it possible that each solar system is actually an atom in some physical system? Our solar system could be analogous to oxygen.
Again, because we're calling it an 8, because we arbitrarily determined there's 8 planets. Yeah, for sure.
While
For
others
sure.
could be analogous to chlorine, iron, or uranium. In fact, the universe we see through our telescopes could be nothing more than a collection of billions of atoms in a larger universe. What about...
I mean, technically, everything we see through our telescopes is a collection of billions of atoms in a larger universe. It's billions and billions and billions of atoms.
about applying this idea of an atom to the whole universe? Well, that idea looks a lot less impossible when you think that everything known to us consists of the same electron.
What? What? I would... how do you take one hard to swallow, extremely unlikely claim, especially given this preamble that makes no sense whatsoever, and you take this extremely unlikely claim and then back it up with an even more unlikely claim? Like, what? What are you doing?
This has moved scientists to explore the idea that every electron in the universe is actually a single particle that moves back and forth in time.
Oh, it goes back and forth in time now, too. Okay. Okay. I'm sure all the serious scientists are absolutely looking into this. For sure. 100%.
There is a lot of complicated math involved, but it answers some of quantum physics' most difficult unanswered questions. John Archibald Wheeler, a theoretical physicist who worked on the hydrogen bomb at Los Alamos and later taught at Princeton, devised the theory. In the 1940s and 1950s, he was largely credited with reigniting interest in general relativity. The idea that every electron is...
Did interest in general relativity fall off in the 1940s and 50s? I know we were all getting super excited about quantum theory, about nuclear physics, but general relativity was still pretty new. We were still discovering there was a universe at that point. It was bright and shiny, and I don't know, whatever.
The same electron is known as the one-electron theory. So what is this theory about? One of the main reasons...
Is that a theory, though? Like, to be a theory, you have to substantiate a thing. It has to pass a whole lot of rigorous testing. It sounds to me more like the one-electron, crazy off-the-cuff idea.
Wheeler proposed this theory is that every electron looks exactly the same. They're all the same mass and electric charge. This ultimately...
Okay, I'm convinced. That was a compelling argument. All electrons look the same. First of all, what do you mean by look? We have never seen an electron. We can't see electrons because they're so small. Like I was saying earlier, they're the same size as photons. You can't reflect light off of them to see them. But let's assume he's saying see euphemistically. Okay. So every electron has the same properties as every other electron. Does that mean they're interchangeable, that they're the same? It's like you go to a brick factory, right? And you look at all these bricks, and they're all the same mass, and the same dimensions, and the same texture, and the same color. They're indistinguishable from each other. Therefore, they're all the same brick, right? And furthermore, if they're going backwards and forwards through time so that they can occupy multiple spaces on this brick assembly line. Yeah, that's the most reasonable conclusion.
Means that distinguishing electrons is impossible. So it's not surprising that Wheeler came up with the idea that if all electrons look and act the same, they might be the same electron. And
okay, no disrespect to Professor Wheeler, because I'm sure whoever wrote the script is completely misinterpreting what he said. But you make the case that because you can't tell the difference means they are the same. Have you ever met twins? Like, some twins go out of their way to be able to make it easy for other people to tell them apart. But if you come across a set of twins or triplets or quadruplets or what have you, and they're trying to do the thing that only they can do, to dress exactly alike, to have the hair exactly the same, whatever. The fact you can't tell them apart, does that make them the same person? Of course not. Our inability to distinguish between things doesn't confer some type of multiplicative status on a thing. No, there's no reason to think so. And there's a lot of reason to think not, because that is not how anything works.
Proposing that the entire universe contains only one electron may not seem so absurd when we consider that the only difference is in our understanding of what an electron is. In practice, everything would remain unchanged.
Then what is the theory for? If it doesn't change anything, then what is the purpose of the concept? What does it explain? What does it solve? What does it help us with? And what information supports it? You need more than, well, you can't prove it isn't the case, because we have no reason to think so. That's the basic level of skepticism, and that is the fundamental bedrock on which science should be founded. You can't just throw out a, hey, wouldn't it be cool if, and call it science. What the hell, man?
To the one electron theory, just as an electron can be bounced around in space when struck by light, it may also be able to bounce backward in time.
How does that make sense? If you hit an electron with an equally sized charged field of energy, it will react to that. Therefore, it could possibly move through time too. That does not follow even a little bit.
As a result, electrons moving backward in time are positrons, the antimatter component of electrons.
Okay, no. I feel like I have to jump in a lot here, but it's like every single thing that's being stated is very wrong. It's pretty hilarious. So positrons are not a component of electrons. Positrons are the antimatter equivalent. They're the opposite. They have the same mass and the same general properties, but the opposite electromagnetic charge. The same thing is true with protons. A proton is a mass with a +1 charge. An antiproton is an identical mass, but with a -1 charge, just like an electron has a -1 charge. With a positron, it's just like an electron, but it has a +1 charge, like a proton would, except it's effectively an electron. They are opposite. When they interact, they will annihilate into gamma rays. That does not mean that the positron is going backwards in time just because it has the opposite charge. That doesn't make any sense at all.
Not only are all electrons the same, but all positrons are the same electron moving backward.
Okay, so yeah, sure, why not? Every electron is the same electron. Every positron is the same positron. And the positron is also the electron, and somehow moving backwards through time reverses your charge. Because reasons.
But what does this theory connote or suggest? Let's start like this. It is estimated that the universe contains 10 to the power of 80 atoms. We can simplify the number of electrons in the universe to around 10 to the power of 80 if we ignore the fact that many atoms have more than one electron.
Yes, let's ignore that really important, crucial to the function of the universe detail. Let's just sweep that aside. Okay.
Although
Ignored.
electrons are theoretically treated as stable, the experimental lower bound of the electron's mean lifetime is frequently given as 6.6 times 10 raised to the power of 28 years. We can use this to see how this theory works in practice. According to the theory and these numbers, the universe...
I'm not even going to look up these numbers. It's just going to upset me. It really is. Because every single thing they've said so far, every assertion, every claim has been highly questionable. So I am very suspect of these numbers, but I'm willing to allow them just for the sake of argument so that I don't give myself apoplexy here.
The universe's one electron has traveled through it 10 raised to the power of 80 times, each time taking 460 septillion years. We can double these numbers.
Like, how do you get that number of years?
But for each time the electron had to travel back in time, resulting in the one electron theory's one electron being at 10 raised to the power of 105 years old. This theory, however, is not without its flaws.
You don't say.
If a single electron travels forward through time as an electron and backward as a positron, there should be the same number of positrons as electrons at any given point.
But why? Like, just because under this hypothesis, you've got an electron going forwards as an electron, and then zipping back as a proton, and then orbiting a different atom as an electron, and then zipping back as a positron, and then orbiting a different atom. First of all, why is it going to different atoms every time? How does it know? How does it keep things sorted out? How does every atom have the same electron? But what if an atom has multiple electrons? If a helium has 2 electrons, and they're the same electron, how does that work? Because you're violating the corollary to two objects cannot occupy the same space at the same time. The corollary is A single object cannot occupy two separate spaces at the same time. But even if the atom somehow had a personal timeline that was removed from the universe, you still only need one positron. I mean, by definition, they are all one positron. So that's all you have anyway. So why would you need more than one?
But that is not the case. The idea is that our universe, with all of its galaxies, stars, and planets, is just one tiny component in a larger structure. This structure, known as a multiverse, would be made up of an infinite number of universes, all existing in their own separate dimensions.
Okay, now we're on to multiverses. All right. It's multiverse is another fun idea, and it actually has a little bit of science behind it. There's some explanations of how it might work, but we have no reason to think it might be the case. We have no way to test it. We have no way to falsify the idea. We have no way to explore any of the claims or assertions. Like the idea that our universe even could be any different than it is, we'd need to examine another universe and see that it is different in order to know that. And we just can't. Not with our current technology, and not in any way that we've been able to think of. So we have no reason to believe there even are other universes. And if there are, it's totally outside the realm of science because we can't investigate it. We can't learn from it. We can't prove or disprove. It's literally just a cool idea, bro. That's as far as it can get. And none of this has anything to do with how our universe is an atom. What are we doing here?
According to multiverse theory, our universe, with its hundreds of billions of galaxies and nearly countless stars spanning tens of billions of light years, may not be the only one. Instead, there could be an entirely separate universe from ours, and another and another. Indeed, there may be an infinite number of universes, each with its own set of physical laws.
There could be. There could also be leprechauns and Loch Ness monsters and Bigfoots and interdimensional aliens. There could be all sorts of things that we have no evidence for and no reason to believe. And they might be true. We can't disprove them. But they have no explanatory power. And we learn nothing from the idea. So, you got anything better?
Collections of stars and galaxies, if stars and galaxies can exist in those universes, and possibly even intelligent civilizations. The concept of the multiverse appears in a few areas of physics and philosophy, but inflation theory is the most prominent example.
What is inflation? Oh, you know what? Well, maybe he'll give us more information. But I'm not seeing how inflation theory has anything to do with a multiverse hypothesis.
Inflation theory describes a fictitious event that occurred when our...
Hold on now. Hold on. You do not get to make this entire video throwing out a whole bunch of made-up, unfalsifiable, unscientific concepts and just drop them as if they're fact or at least being studied seriously, and then come to one of the most mathematically well-established facets of the Big Bang Theory and call it fictitious. Now, I'm not a fan of inflationary theory. The hypothesis bugs me because I don't like the idea that the universe just arbitrarily went boop and then slowed down. But the thing of it is, the universe is still expanding. It's still inflating, just at a much reduced rate from that ultra brief moment of time when it went several orders of magnitude in an instant. And we have good reason to support that idea. It's not just a slap tape on a theory to explain something we couldn't otherwise explain. It's not a god of the gaps of physics. We can see mechanisms that could cause it, like the condensation of matter out of an energy state that would drive space apart very, very rapidly, as a one for example. So there's some science to it. It's not, it may be incorrect. We may learn more and find out that what we think happened was not the case. We could learn the entire Big Bang was erroneous. And that would be wonderful if we did, because we'd learn more about the sciences. We'd understand how our universe works better. But demonstrating that it's incorrect is not the same as it's fictitious. And it's super, super ironic that after this whole video full of all this wishful thinking crap, you take something that is established in math and science and call it fictitious. My leprechaun friends want to have some words with you.
The universe was only a fraction of a second old. The universe experienced a period of rapid inflation, inflating to become many orders of magnitude larger than its previous size in an extremely short period of time. Our universe's inflation is thought to have ended around 14 billion years ago. However,
rapid inflation ended. Inflation took place a fraction of a second after the Big Bang and lasted for a fraction of a second. But that rapid inflation, that's just fast expansion. Now we have slow expansion. It's still inflation. It's still expanding. It's just at a much reduced rate. And the fact that that rate changed shows that the rate can change. So that's valuable data.
Inflation does not end everywhere at the same time. It is possible that as one region's inflation ends, another region's will continue. Thus, while inflation ended in our universe, it is possible that inflation continued and continues even today in other much more distant regions. Individually,
if it ended in our universe but continues in more distant regions, I'm not sure what he's trying to say here. Is he saying that our universe kind of bubbled off, like inflation started, and then what determines our universe was that it stopped the rapid inflation, and so it kind of sealed itself away from the other universes? Universi? Universe tree? I don't know, but it bubbled itself away, and then inflation just continues to go off out there in the cosmos? Or is he saying that pockets of inflation within our universe that didn't stop sealed themselves off? Or like, what's the mechanism here? I don't understand.
Universes can pinch off from larger inflating, expanding universes, resulting in an infinite sea of eternal inflation teeming with countless individual universes.
Okay, so it's like a kid with a bubble wand. You've got the kid blowing, and bubbles pop out. And every so often, a bubble reaches a certain semi-stable size, and then it closes back up and drifts off, and then the next bubble begins to form. It's all the same wind, it's all the same inflation, but it's blowing universe bubbles out of the bubble soap of existence, realityness, something like that. Now, please understand that that's an off-the-cuff model. I'm not suggesting that there's some god being blowing a bubble wand out there somewhere. I know someone will make a religion out of it if I don't specify.
In this eternal inflation scenario, each universe would emerge with its own physics laws, particle collection, force arrangement, and fundamental constant values. This could explain why our universe has...
Hold on. Is that a Star Trek starship in there? Like, okay, I'm familiar with the graphic. This is a NASA graphic, and in the very center it shows our solar system. You can see Jupiter and Saturn clearly, and if you look closely, you can see Earth. And and then the gas around it gradually feeds back into the Milky Way, our galaxy, up at the very top, and next to it is Andromeda, and then there's other galaxies, and they get smaller and smaller as you go all the way back to the cosmic microwave background, and then there's blackness, and then the outer shell, which is the moment of the Big Bang, which is weirdly kind of the opposite of how the universe actually works, but it's great for a visual aid, right? But then, going towards the upper right, it looks like a Federation starship for some reason. Why is that there? What's going on?
The properties it does, particularly those that are difficult to explain using basic physics, such as dark matter or the cosmological constant.
All right, folks, I'm going to wrap this one up because it's getting a little bit long and it's getting really hard to edit. There's a lot of extraneous stuff going on, and it's going to make it an absolute nightmare to chop this up. So let's end this here. If there's interest in a part 2, I may finish it up, but I think we've hit most of the major points, and I don't see a lot of value in continuing on because so far we haven't had any solid science. It's just been assertion upon assertion upon assertion and nothing to back it up, and it's been very silly. Been very, very silly. So we're slightly more than halfway through this video. So if you would like to see a part 2, let me know down in the comments. But I think overall, there's been no case presented for how the universe is an atom, and anything that's had anything to do with atoms has been laughably ridiculous. So, I don't know. It's fun, it's amusing, but there's not a lot of scientific value here. So it's up to you. Let me know what you think. In the meantime, thank you guys so much for watching. Thank you, those of you who are new, for subscribing. It makes a big deal to a channel like this. And as always, stay curious.